Welcome to the Ventura County Astronomical Society's General Meeting. My name is Reza, and I'm the Vice President of Orange County Astronomers. OCA is happy to join forces with VCAS to make this event happen. Before we start the main talk, I would like to point out to you the ways in which you can interact with us. First is the raise hand function. Please go ahead and find the raise hand button and click on it. This is how we're going to applaud our speaker shortly. Excellent. I see people all doing the raise hand. Thank you. Look for the chat menu item. This is how you can send us any comments you may have. And third and last, please find the Q&A option on your screen and look for the Ask a Question button. This is where you can ask our speaker questions during and after his presentation. With this, I'm handing it over to Keith to introduce tonight's speaker. Keith.
Reza, once again, it is always a pleasure to be with you and to join forces with OCA as we peek into the skies and further the hobby and pastime and science of amateur and professional astronomy. Before I introduce our speaker tonight, as you can see, I'm surrounded by a number of people. David Contreras, our Vice President of Programs, has joined us tonight. He's been on the front line in this COVID battle. He is just now getting time to breathe, and he's lining up our program starting in September of speakers. We are going to take a hiatus in the summer. David's working on that now, and I can assure you, come September, we are going to be live back at the Moore Park College Forum and have a great lineup of people ready for you. Also with me tonight is Janelle Harmon. She is our newest member of the board. Now, you all remember Beth Riggs, our membership coordinator. She had a fantastic employment opportunity in Montana. So, not being able to do the meet and greet in person, Janelle Harmon stepped up, and I want to introduce to you Janelle Harmon, our newest membership coordinator and member of the VCAS board. Let's have a hand for Janelle Harmon. Janelle, say hello to everybody.
Hello, everyone. Glad to meet you all and glad to hold this position.
Okay, I'm joined by two other people tonight. You all will recognize Todd Mitchell, who did a phenomenal job of putting together this year's 50th anniversary calendar for VCAS, which coincidentally featured a number of pictures from the Thatcher Observatory, which we will be talking about tonight. And he is the one who actually gave me the tip for Dr. John Swift, who will talk about the Thatcher Museum. And of course, I'm also joined by John Rogers, who actually has been around with VCAS for so long. When Thatcher was brand new, he got to use it a little bit, and maybe in the question and answer period, he may get a chance to share a little bit of his experience actually on the grounds of the Thatcher Observatory. Now, to our guest speaker, Dr. John Swift. Let me start with the background. In 1965, UCLA and Caltech brought the Thatcher facility to Ojai as part of a summer science program for high-achieving students. At that time, a very young VCAS would have had its star parties somewhere on the grounds, and John Rogers was definitely a part of that. But after the departure of the program and through the passing years, the observatory went into, let's say, some disuse, and I hear that it was even used as a dormitory for some of the facility. Well, Dr. John Swift is here with us tonight. He will talk about how he transformed the Thatcher back to a world-class astronomy research facility. His efforts have been featured on shows such as the PBS show, The SoCal Wanderer, and tonight he brings his story of how he transformed the Thatcher Observatory back into a world-class facility tonight. Dr. John Swift, please.
Thank you for that introduction, Keith. Yes, I'm delighted. Thank you for the invitation to be part of this and to give a little presentation to the VCAS and whoever else is out there in cyberland. Indeed, the Thatcher Observatory has a crazy history that I'll talk a bit about tonight. And I think I've kind of ordered this talk sort of chronologically. So I'll take you through a deep history and then talk about some really important kind of benchmark moments in the history of the facility, and then talk about how I've come to renovate the observatory, and also I'll show you some of the programs that we're now engaged in at the school. The person who really understands this history better than me is the department chair, the science department chair at Thatcher, Dr. Chris Vinal. And he was unable to be here tonight because his daughter is graduating tomorrow from high school, and he has all kinds of things going on. So he would have loved to be here tonight, but I'm going to do my best to not totally butcher the history that mostly he uncovered from the Caltech archives and the Huntington Library and our own archives on campus. So without further ado, I'm going to start my slideshow, and I believe that Reza is going to be moderating the chat through the talk. And Reza, I want to just give you permission, if there's an interesting question or comment, you can go ahead and interrupt me at any point, because I think I'm not super familiar with the audience, and so if people have particular questions that I may not be covering, I'm totally happy to take those in stride.
Great, will do. Thank you.
Awesome. So let me share my screen here. And I wanted to also give you on this front page here, down in the bottom left, we have a website actually that contains a lot of information about the observatory. I encourage you to go check that out, thatcherobservatory.org. And we also have an Instagram account where we post some astrophotography pictures, some science results, some fun activities that we're doing. And you know, in the world of COVID, we've really not had any visitors on campus. We've been pretty locked down for the last year. But if things hopefully keep going in the right direction, we're hoping to have you know, open houses where the public can come and enjoy the facility that we have up here on the hill. So keep that in mind, and you can contact us through our website, Thatcher Observatory, or direct message on Instagram, and we'll get you on the email list to let you know about events that are upcoming. So my background is not the focus of this talk, but I thought I would just talk a little bit about my background as it is relevant to the renovation of the Thatcher Observatory. In 2012 through 2014, I was doing a postdoc at Caltech, doing research in exoplanets using mostly the Kepler data. The Kepler Space Telescope was flying then, and it was really transforming the way that we view our place in the universe by discovering thousands of exoplanets. And at the same time, I was also project managing the brainchild of Professor John Asher Johnson, who was at Caltech at the time, a exoplanet observatory called Minerva, and which was using off-the-shelf technology to collect light, basically, to feed into a very, very expensive and high precision spectrograph. And so take a note of these telescopes here, that this is now on the Caltech campus there. You will notice that they look very similar to the ones, the one that is in Thatcher Observatory. So at Caltech, I actually got an invitation to be a visiting scholar at the Thatcher School in March of 2013. And I came to campus, I looked around, I gave lectures. This is me giving a talk to a bunch of students and faculty. I did some guest lectures in classes and things like that. And I learned about the observatory. If you know anything about the Thatcher School, it makes perfect sense that I would visit the observatory on horseback. Thatcher's pretty famous for its horse program. We have 126 or so horses on campus, and all the freshmen go through the whole horse program where they're taken care of and learning to ride horses. Very interesting, and it's actually a very powerful experience for high school age kids. So I saw this observatory, and as Keith mentioned, it was in not a very good state. I mean, there was kind of some makeshift telescope in there, and it wasn't really being used. And it indeed had been used for faculty housing. And in fact, our current head of our school used to live in that observatory with her husband. And so there's a really funny kind of moment in history that I will actually get into a little bit more later. And then when I was there, I told the head of the school at the time, I said, well, heck, I'm actually doing a lot of market research, and I really understand what it would take to renovate this observatory, because I'm sort of up to speed with all the latest and greatest technology and how much it costs, et cetera, et cetera. And he kind of took note of that, and that was kind of that. And I didn't really think too much more about it at that point. But my relationship with the students at Thatcher actually led to some really interesting internships, where one of the current students at Thatcher and one previous student, an alumni, worked with me at Caltech on this, on Minerva, that exoplanet observatory that I was project managing. And so when I wrote the first paper for Minerva, these two students, Eric Herzig, who was a current student at Thatcher, and Justin Miles, who was an undergrad at Yale, and who is now actually in a PhD program at Stanford in astrophysics. They both ended up on this paper for the work that they did as high school student and as a young undergrad student. So basically at that point, around late 2013, early 2014, Minerva and John Asher Johnson was moving to Harvard. And so I was kind of, packing my bags essentially and getting ready to move the whole operation to being based in Boston. And the facility was going to be moved, instead of Palomar or somewhere that Caltech was affiliated with, it was going to move to Mount Hopkins, which is a whole set of observatories on that mountain that Harvard and Smithsonian Astrophysical Observatory own. So I was basically on my way to Boston, and the head of the school contacted me, and the dean of faculty contacted me, and basically said, we're going to give you an offer, for Thatcher. And I was like, oh, okay. And I thought I was charmed, and I thought that was really nice, but I didn't initially take it very seriously until he started talking about really how serious they were about bringing back an astronomy program at Thatcher. At that point, note that I didn't know anything about the history of the Thatcher Observatory. So it turned, long story short, there I was in November 2014, not in Boston, but teaching classes at Thatcher. And it wasn't long after I was there that there were a handful of really enthusiastic students, really capable, really sharp and motivated students at Thatcher. And one in particular, Theo O'Neill, who was a freshman, was really excited about this idea of doing astronomy in high school. And she uncovered something and sent it along via email from the Huntington Library. And she sent this along. And I was like, oh, okay, cool. What is this? Mount Wilson and Palomar Observatories, Dan Crotty, Thatcher. Of course, they spelled Thatcher wrong because everybody does. And I'm reading down and I'm like, okay, December 2nd, 1952, and talking about mirror coatings and all this other business. And I'm like, well, that's kind of cool. Like, so I guess they've been doing astronomy at Thatcher for a while, like since the 1950s. And then I scrolled all the way down to the bottom. Best of luck and Merry Christmas, sincerely, Edwin Hubble. And I'm like, wait a second, like Edwin Hubble, like Edwin Hubble? Like, what in the heck is going on here? And so this was really, this was extraordinarily compelling. And I'm like, what in the heck's going on? So I talked with the people at Thatcher. Even the headmaster at the time had no idea what was going on here. And I'm like, wait, so there was Edwin Hubble was corresponding with Thatcher students in the 1950s, and you have no idea what that's all about. And that blew me away. And it blew away Chris Vinal as well, who had been the chair, and it continues to be the chair of the science department here And I think he'd been chair for at least 5-10 years before this moment. And he knew nothing about it. So so that's kind of like where we sort of dug in. And by we, I mean mostly Chris. And he spent some time down at the Huntington Archives and at the Caltech archives there. I forget what they're called. And he really started digging into why in the heck, how could this possibly be that Edwin Hubble's like talking with students at Thatcher in the 50s, telling them how to coat their mirrors. So I'm going to take you through a kind of abbreviated version of this history, but hopefully I put together a timeline that makes sense, at least. And I want to point you to a paper that Chris and I wrote, such that this history wouldn't be lost ever again. It's A Century of Astronomy at the Thatcher School. And there's actually a link to this through the Thatcher Observatory website if you want to just download the PDF and check out all the details. You can fact check me in case I get some things wrong here. But basically, this is kind of how it goes. The beginning, we believe, was a letter that Sherman Thatcher wrote to George Hale in 1906, looking for a letter of recommendation for a prospective student. And through their conversation, he also invited him to come to the Thatcher School and perhaps give a little inspiration to the boys. So then, and I don't understand this date discrepancy. And this is 6 years later that there's record of letters being written. And of course, this is 1912. So I don't know, maybe they were just riding mules back and forth between, Pasadena and Ojai. But at any rate, the short of it is that George Hale wrote the recommendation or gave the recommendation, and then also agreed to give some talk at some time for his work on the observatory. And this is the Ventura County Astronomical Society. I'm assuming people know who George Hale is. He's well, they call him the grandfather of modern astrophysics. He was into building the largest telescope in the world, which he did 4 times over, right? In the 40-inch Yerkes Observatory refractor was the largest telescope ever built at the time. I think that was in the late 1800s. And then the 60-inch on Mount Wilson was also the largest telescope in the world. That was 1908 or somewhere around there. And then at the time of these letters going back and forth, this is when the Hooker telescope, the 100-inch, was being built, and that was also the largest telescope in the world at the time. And so he agreed to come and give some talks to Thatcher, and there was a whole bunch of other stuff going on at the time. One of which that is relevant to the Thatcher Observatory is George Hale was interested in bringing Robert Millikan out from the East Coast to Caltech. And as part of that, sort of convincing him that it would be a good idea, he was thinking of getting Robert Millikan's son, Glenn, into the Thatcher School as being kind of part of ensuring that it would be a good idea for Robert Millikan to come out and be a permanent part of the Caltech faculty. And so there's a picture here. So that's George Hale in the middle, and Millikan, and then Arthur Noyes, actually. So here's some really high, heavy hitters in the science world. And so in the end, Millikan agreed to come out, and Glenn indeed did come to Thatcher. And in addition to that, the Thatcher School was being incorporated at the time, and they were starting a board of trustees. And Sherman Thatcher wrote to either Millikan or Hale, but basically asking Robert Millikan to be part of the board of trustees at the school. And his response was basically like, sure, yeah, I'll do it maybe for a year or so. Like, that would be cool. I like what you're doing at the school. So why don't we do that? Now, in the end, Robert Millikan was on our first board of trustees, and he actually continued on the board of trustees for 30 years until he died in 1953. And in 1923, actually, so maybe for those of you who don't know Robert Millikan, he is a Nobel Prize winning physicist he won the Nobel Prize for measuring the charge of an electron with his famous oil drop experiments. And the Millikan Library at Caltech is designed, the architecture is designed to in appreciation of the oil drop experiment. And the year that he got the Nobel Prize, 1923, right? So here's a fresh Nobel Prize winning physicist on the first board of trustees at the Thatcher School. So also, knowing that the illustrious folk that were coming through Caltech, Sherman Thatcher also invited this guy that everyone recognizes, I'm sure, Albert Einstein, to the Thatcher School. And it actually almost happened. It was very, very close. It was a board of trustees meeting, and Millikan was supposed to be there, and Albert Einstein was supposed to come with him, but I don't know exactly what happened, but they didn't make it. Instead of coming, Albert Einstein gave an autographed portrait of himself to the school that we still have, and which says, in German, by the way, it says, "To be undemanding and independent, that is freedom." And so that was the near miss of having Albert Einstein on the Thatcher campus in the 1920s. So going down the list of this crazy history that's sort of notable and potentially interesting is another scientist of similar caliber who probably would have won a Nobel Prize if astronomy was actually considered for Nobel Prizes back in the day, and that is Edwin Hubble. And what we learned is that in 1942, he actually gave the commencement address. And so this was like 6 months or so after the Pearl Harbor attacks. And so his whole commencement address was geared around the war, and it was titled "The Years Ahead." And basically that was the connection there that led to the correspondence between Hubble and Dan Crotty several years later. So that kind of that tied up that sort of history in a nutshell for us, that made us understand in a lot more detail exactly how this letter came to be. And Chris and I actually had the pleasure of meeting Dan Crotty. We looked him up and found him. He lives in Ventura, and we interviewed him and we talked with him in depth about that experience. And he was actually from Pasadena and was one of Hubble's neighbors. So there was more kind of going on there, and so kind of a cool history, and really kind of puts into perspective the importance of the Thatcher Observatory. And yeah, there's several other points that I'm missing here, but I encourage you to go check out that paper for more of those details. So moving from kind of the ancient history to a more recent history that leads up to almost the current era is the summer science program era. And the summer science program was started in 1959. I imagine not totally disconnected from the Sputnik launch and the sort of ensuing panic that Russians were sending things into space and we weren't. And the summer science program, as I understand it, was really kind of built to be a feeder to Caltech or just technical colleges to prepare students for really highly technical fields. And Newton Chase, who was our headmaster at the time, was totally on board with this idea. And so it happened. We have 480 acres here up in the east end of Ojai Valley, and it's quite dark. We have the Los Padres National Forest to the north. So really 180 degrees of azimuth to the north is really pristine skies. The mountains are about, they get up to about 18 degrees of obscuration, but beyond that, we have pristine skies in the north, and it's really quite a good observing location if you don't care too much about seeing. So that happened, and then there was no telescope at the time. I'm not sure what they did in those first few years. I'm sure they probably brought telescopes up and did work up there, probably camped up there. And it wasn't until 1965 that George Abell, who was a professor at UCLA, secured funds through NASA to build a legitimate observatory up on the hill. And they had the telescope built at Caltech, the 24-inch astrograph, and there was a lot of great science that was actually done with that telescope, in addition to the summer science program. So I've never been super clear about what was going on with this observatory in its original form, other than the summer science program. But being, having spent time in academia, I would imagine that George Abell wanted a place to send graduate students and train them up. And LA at the time was definitely not the place to do that. So it's a little bit of a mystery exactly what was being done, for 9 months out of the year when the summer science program wasn't actively using that facility. But we have some documentation. This picture is from our magazine, the Thatcher magazine, and this is a picture of George Abell there in the middle, and some students probably posing. I mean, the kids looking through. I think they're probably looking right at the dome, but it makes for a good picture. And the summer science program has been one of the most successful high school level summer programs, particularly in science, and it's still continuing today. Very successful. They actually have multiple programs on multiple campuses around the West. And it was a collaboration originally between Thatcher, Caltech, UCLA, the Claremont colleges, Stanford University. And it existed on the Thatcher campus for 40 years. And then in 1999, it was an interesting arrangement, actually. And I think the fatal flaw in terms of having the summer science program on Thatcher campus was that Thatcher never hired anybody that knew anything about astronomy. So we were completely beholden to the people that used the facility. And when they weren't around, nothing was, the students didn't benefit from that observatory. The faculty didn't benefit from that observatory. It was just kind of this thing that was up on the hill. And I talked with many alumni from Thatcher that knew the observatory was there, never used it, never saw it, never stepped inside. And so it became this thing where Thatcher was kind of taking care of all the administration and, all paying all the bills and hosting this facility. And then other people were just coming in and using it. And there was no real feedback loop that made it mutually beneficial. A lot of that is my own sort of stitching together of the story. But the fact of the matter is that in 1999, they pulled funding and they redirected funds that they were using to support the observatory into other channels. And so the summer science program yanked everything out and took their facility to actually a neighboring school for a while, the Happy Valley School, which is now called Besant Hill. And the observatory was repurposed as faculty housing, and basically all of the astronomy and the legacy that had been built, for decades just kind of ended. So that's kind of what leads us to the current, recent history here of, this is where I come in. And so like I said earlier, when I visited the Thatcher Observatory, it was very clear to me immediately what it would take to renovate that observatory and make it something actually really useful that you could build, say, curriculum around at the school. And this is the Minerva test facility. Minerva actually is comprised of 2 of these like clamshell structures with 4 telescopes total. And the way that works is that the 4 telescopes actually, the focus is there's a octagonal fiber optic cable that sits at the focal point of each one of those 4 telescopes. And the starlight is then, shot down this fiber optic cable and then injected into a stabilized high precision spectrograph. And the 4 fibers make like a pseudo slit for the spectrograph. And it was made to be a radial velocity exoplanet detection facility. So I worked with PlaneWave quite closely in doing some quality control and some, going back and forth with them. As PlaneWave was breaking into the professional market, or at least the higher level markets in the telescope world, they were awesome. They were such great people. They were so willing to work with us. They were excited about what we were doing. They were also just kind of right down the road in Rancho Dominguez. So a lot of what happened with the CDK 700s at the time was in conjunction with the development of the Minerva Observatory. And I basically, had all these pieces in mind for the Thatcher Observatory, and one of which was the CDK 700. So after we were able to raise funds, we put together about $500,000. We got a new dome. We got a CDK 700. And this is us in the fall of 2016, wiring up the observatory and putting all the pieces in place. It's kind of cool. It was really fun to watch this all come together. This picture on the left here is when we got the new dome, and then they had to crane the telescope through the slit of the dome, and these really amazing, competent construction folks. It was really awesome to just watch this whole thing come together. So super exciting stuff for me. And this is our first light ceremony on December 10th, 2016. And we had a bunch of people up there. We gave some talks and had some food and took our first light image, which is this galaxy. Probably some of you recognize it. This is the fireworks galaxy. And this was taken in, these are science filters. So it's what gives it a kind of a funny hue. These are taken in Sloan second generation GRI Z bands. So it doesn't have the LRGB, true color nature to it. But for us, this was the very first image that we took, and it was awesome. It was a big moment. So this is what the new facility looks like. This is the CDK 700 sitting in the dome. We had to put a new pier on the thing. We had to actually extend the pier because this is an Alt-Az telescope, and the original telescope was a equatorial mount, which was offset and took up a lot of space. And so some of the key components of the renovation were, well, I'd say the key component is that the whole facility is automated. Okay, it's robotic in the sense that I can control it from my phone, and there's remote control of the whole facility, but it's also totally automated, and that is absolutely essential for us because we have pretty packed schedules here, and the students do too. And there's no way we're staying up all night observing things, multiple nights of the week. And so we have a little all sky camera, and this is just a little video showing the observatory doing its thing all night long while we're in bed snoring, and we wake up in the morning. Well, we program the scheduler and we prioritize the projects that we want, and the science that we feel is most valuable, and then the dispatch scheduler just figures out what the optimal time is to observe the sources and goes through the whole night. And in the morning we wake up, and now I actually have an automated pipeline as well. So all the calibrated data just shoots into our archive, and then we can immediately start doing analyses in the morning. So that was huge, and it was a big effort, and it's a beautiful facility that we're all kind of really excited about. So now we have the facility, right? And then the question is, what are you going to do with it? And so this is where the building a program part comes in. And it's been a big effort, and it's still actually evolving. But I've taken a bit of a different approach to how I'm inspiring the students to become involved and to learn some physics, astronomy, coding skills. And the learning objectives are they're as soft skill based as they are hard skill based. So some of the things that I really try to focus on are things like critical thinking, problem solving, data analysis, programming, time management, leadership, responsibility, and then of course all of the foundational pieces that you need in order to understand the astronomy. But the point here, though, in ordering it this way is that I my work here, I'm not so interested in creating astrophysicists. That's not necessarily what we're doing. I mean, actually, we have a couple that are probably going to turn out that way. But the point here is that these kind of real world skills are transferable really to any endeavor that these students may involve themselves in. And so really it's kind of giving students a glimpse into what it's like to actually be part of a team that is producing results that aren't just out of a textbook and that don't necessarily have well-defined answers. And all of those hard skills and soft skills that go into that are things that these students carry with them, after they graduate, regardless of what field they end up in. And so the way that the program is kind of scheduled, structured, is that we kind of just start at the top, right? The first thing that we kind of lure the students in with is not like, here's Newton's law of gravity or whatever, and here's the equation for whatever, blah blah blah. But we actually just start with like, do you want to find a supernova? Right? We start with the questions that actually have meaning, that people can relate to, and that motivate the learning that is necessary to do this with any level of competence. And so there's there's tiers going up. We don't need to kind of get into these details too in depth, but and this is the part where I'm still kind of building out how this actually works at the school, to involve people that have all kind of levels of experience and skill and levels of interest, because we don't expect a large fraction of our student body to actually do astronomy research. I mean, it'd be great, but I mean, I don't think just the demographics doesn't work that way. And that's great. That's fine. That's it's something that we want everybody to benefit from. So there's all kinds of levels that lead you up to perhaps finding a supernova. Yeah, I'll skip over some of these. So another really important facet of this is really giving access to the students to be involved in science. And this does not necessarily mean, having to do the data reductions and the analyses and, coding, but also just even the appreciation, right? The appreciation of the fact that, that our atmosphere is transparent in the visible bands, and allows us to see the origins of our solar system and our Earth, right? Just with our own eyes, and to build that connection, right, to the dark skies, to our origins. And so we do all kinds of things where we take students to talks. This is in the bottom left here is one of these public talks that the Las Cumbres Observatory gives, one of their talk series. And this was actually an important one for us. This is Tabby BOYAJIAN here in the kind of the middle. And we had a huge number of students that went to that talk. We're super inspired, and we actually are continuing to monitor BOYAJIAN'S star today, 4 years later. We have like group meetings where students are presenting their results and the things that they're into, what their projects are, to their peers and other faculty members. We visit observatories. This is actually the Minerva site. So this is that clamshell structure that I showed you earlier. This is one of those there. And this is John Asher Johnson here, giving us a little overview of the facility. And in this top right panel, these are actually 4 Thatcher students at an American Astronomical Society meeting, where they presented their results and got to interact with the professional community. So these are the kinds of things that I think are really valuable for our students to be involved and to be engaged. And then obviously some of them really kind of catch a flame and really take their science knowledge and skills and everything to the next level, which is inspiring to see. Okay, so I don't know how much time we have left here, but this is, for me, this is the fun stuff now. So we have a facility, we have a working program that's evolving. We have student buy-in, we have a lot of people interested, we have a community that's interested. And so, what is it that we really do? And like I said before, we kind of start at the top. And so even from the beginning, I came in immediately establishing research programs with the facility. And I did this through my my contacts in the professional community, and reaching out to friends of mine and people I know who may have, situations that would be mutually beneficial for us and them to involve students at all levels. My background is in eclipses and transits, so this was something that was easy for me to start and continue when I got here. But it's been really awesome to reach out to friends and get into fields of research that I haven't, been in, and I get to learn all kinds of really fun new stuff for myself too, which is great. And so aside from just the research, we also have a budding astrophotography program, which is really taking off. And it's next year is going to be a really big year for us in astrophotography. And I'm really excited about that. This might be of interest to some of the VCAS folks. And there may be even some room here for some feedback and collaboration and using some of our expertises to benefit from our experiences. So I'll take you through a little bit of what we're doing and kind of where we're contributing to astrophysics. So the first one, and this is the one that I'm most familiar with, are transiting exoplanets. And so what that is when there's a chance alignment of a planetary system in space, such that the planets are orbiting in a way that they'll cross the disk of the star. Then you can witness these dips in brightness of these stars, and they're exoplanets because those dips repeat regularly and they have the same shape. And so that there must be something going around the star that is periodically obscuring the light from the star. Of course, you don't see the planets themselves with this method, but it's a very powerful way to discover and characterize exoplanets. And in fact, the vast majority of exoplanets that are known today were discovered with this method. And so we have demonstrated our ability to take really high precision photometry and to characterize transiting exoplanets. And we've done this in a way that has earned ourselves a spot on the TESS follow-up team. So TESS is the Transiting Exoplanet Survey Satellite that NASA launched a couple years ago. And it is kind of the successor to Kepler. And instead of looking at one patch of sky like Kepler did to do the statistics of exoplanets in the galaxy, TESS has kind of got a complementary approach where it's surveying the entire sky essentially for shorter periods of time, looking for all of the nearby exoplanets and all of the exoplanets around bright stars that the next generation of telescope like James Webb Space Telescope, the next generation of missions will be able to follow up and get more in-depth information, perhaps even learning about whether or not life exists on these nearby planets. So it's a huge amount of data. And as NASA learned with the Kepler mission, the best way to go about doing this is not to make it proprietary, but to make it completely wide open. And so we're on the team that actually follows up these targets and validates their ephemerides, like figures out, really nails down what the periods and the timing of the transits are, and also discerns which stars are really having transiting exoplanets, which ones are false positives, et cetera, et cetera. One of the challenges with TESS is that the pixel sizes are huge, and because they're with one shot, I actually forget the exact numbers here, but one shot, TESS can get an enormous swath of sky. I think it's like 90 degrees by 10 degrees or something like that. So, I don't know, something like 1,000 square degrees of order in one shot. But, so one of the compromises there is that the pixel sizes are huge. And so this is showing an image from TESS, and it's showing the pixels that are being used to generate a light curve. But anyone that's looked close at any pictures of our galaxy knows that there could be 5 stars actually in those pixels right there. And so they need follow-up observations, mostly ground-based, to figure out which star is actually it has a transiting exoplanet, or if it has a transiting exoplanet. And so that's one of the things that we do. And this would be one demonstration of a light curve that we produced at Thatcher Observatory that gives us a sense for what our capabilities are. So this is just relative brightness of a star as a function of time. And the mid transit time, or the expected mid transit time here, is at 0. And you see a lot of scatter on the left-hand side and less scatter on the right-hand side. That's because this was it was a low source. There's a very high air mass on the left here. And as it rose, we got better and better photometric precision. But if you look here on the right-hand side, over the course of about an hour and a half, we're getting 0.1% precision on a 12th magnitude star with 90-second exposure times. And that's kind of like basically our benchmark for like what we can do in terms of photometric precision. So we're really engaged in this work now with TESS, and we just actually have submitted some data recently. So this is a very recent submission, and the TESS team, this is on the right, are the light curves that we actually submit to TESS. They like us to use a particular software for generating our light curves, but we also do everything custom as well and validate for ourselves that we trust these results. And so this is the same transit on the left and the right. And you can see here, actually, this is an interesting example of the depth of the transit was exactly what was expected, but you can see where the predicted times for ingress and egress when the planet enters the disk of the star and where it exits is a little bit off. And so we were able to correct this ephemeris by a few minutes with our data. And that's the ephemeris thing is a really important point, because TESS only spends so much time on one area of the sky. And so if you get an ephemeris for a particular transiting exoplanet and you kind of just put it on the back burner for a few years, if the errors in the ephemeris could potentially make it so that you won't be able to find it again. And so by updating the ephemerides of these transits, it allows the possibility of follow-up study further and further in the future. And so we're kind of securing these sources as potential studies. That's by updating the timing of these things. So that's kind of the overview of the transit work that we do. We also have a really interesting supernova search program. And these are some images from our search program. And we're working on this project in collaboration with an old grad school friend of mine, Ryan FOLEY, who's at the University of California, Santa Cruz. And he's one of the world experts on supernovae, type 1a supernovae in particular. And here he is, the next to last on the right here. And this is his research group. I think it's actually his research group has evolved a little bit since this picture. But Charlie Kilpatrick, I think, is going to Northwestern. I think he's got a position there. Dave Coulter here, who is the guy who found the first kilonova, the colliding neutron stars. Dave Coulter was actually the one that found the optical counterpart to that, which was pretty exciting. And Cesar, and there's a couple other people here that I don't know, but a really fantastic group. And they've been so gracious in lending their expertise and working with our students. In fact, some of our students do summer internships in the FOLEY research group at Santa Cruz. And this has been absolutely essential for us because I know about supernovae and I understand them. I understand the physics behind them, but definitely not ever done research with them. And so their expertise is instrumental in really keeping us on track and producing useful science. So of course, the first thing that we wanted to do is to demonstrate that we could find a supernova. And so we started surveying nearby galaxies and just basically taking difference images and seeing if anything showed up. The frequency of supernovae in a typical galaxy, like I say, this Milky Way type galaxy, is something like once every 500 years or something like that. So, so you can imagine if you do the statistics, if you think about this statistically, that means that if you survey 500 galaxies, 500 sort of Milky Way sized galaxies for 1 year, you should actually detect a supernova, statistically speaking. And so we actually have actually 2,000, I think, galaxies in our queue, although we haven't observed that many yet. But we have hundreds that we have observed and thousands in our queue that we're basically just surveying whenever we have gaps in our observing time. And so you look at galaxies like this, and then of course you just look for the red arrow up in the sky, and those always seem to point to the supernovae. And this was actually a really fun one because this was the first supernova that we discovered. And while we did discover it ourselves, we didn't actually discover it because other groups had discovered it before us, so we don't get the discovery of it. But this really demonstrated to us that this was a viable program, and it was super exciting. It was like one of these moments where we were working on our pipeline, our data pipeline, and we happened to pick this galaxy to work on our pipeline with, doing subtracted images and seeing what pops out. And this supernova actually popped out, and I kept saying like, okay, something's wrong. Like, what's wrong with the analysis? Because, and it took us like 5 minutes before I realized like, no, that's actually like a real supernova. So this was super fun. And we have yet to just actually discover a supernova ourselves, but we sit in this interesting window kind of between the Canaries and Hawaii, where Pan-STARRS survey is taking place, where we have this like couple-hour window where there's a possibility that we will actually discover a nearby supernova in the next couple years. If we have to, the timing has to be just right, but it is possible. And so that's this thing runs in the background, and this is one of the things that we're hoping will pay off here in the next year or two. In the meantime, before we discover these things, we're refining our follow-up program for supernovae. So once a supernova is discovered, it's triggered, by space satellites, whatever it may be. Mostly the FOLEY group does this vetting for us, although we do poke around and see if we can find things that are worthy of follow-up. Then we really lend our our possibility of doing continuous observations of these things to the professional community. Typically, supernova light curves are not this well sampled. And so we can hop on these objects really early on. This is, let's see, what's this? This is like 2 weeks between lines here. So this is like a week and a half or something, 10 days or so, maybe a little more than that before peak light. So we get to watch the rise curves of these supernovae and then see how they fall in different photometric bands. And the shapes of these light curves encode some really important information about the mass of the progenitors and the situation, the sort of circumstellar environment in which these things actually go off. The overall purpose for this is, for us in particular and for the FOLEY group, is to really understand the type 1a family much better than it has been understood. And this, of course, relates to the use of type 1a supernovae to map out the expansion history of the universe. So these type 1a supernovae, they are actually, it's a pretty more diverse family than you would like, actually. But the essential, the sort of, the basic picture is that you have a binary system where one star went through its asymptotic giant phase, and it's left a remnant, a little white dwarf, the core of the star, in this binary system. And then when the other star in the system starts to evolve, it blows up, and you can get overflow of the envelope of the other star through the Roche lobe, and then to spiral in onto the white dwarf. And so the white dwarf can accrete mass from its partner. Once the white dwarf gets to, what's the Chandrasekhar mass is like 1.4, I think. I forget. Probably should know that number. But Once the white dwarf gets to a certain mass, then it becomes unstable because of the way that the star is being supported. It's being supported by this really weird quantum mechanical effect, actually called degeneracy pressure. And once the star gets to a certain mass, it can no longer withstand its own gravity, and then it basically turns into a nuclear bomb. The whole thing just detonates. And these things can be the brightest things in the universe for short amounts of time. And the interesting thing about them is that they all blow up at the same mass. So they're all these nuclear bombs that have the same amount of material in the nuclear bomb. Therefore, the brightness of the explosion kind of has like a wattage on the light bulb. And so then you can observe these type 1As and see how apparently bright they look, and then know how intrinsically bright they are, which then gives you the distance to these things. And this is the primary way that dark energy was discovered by Adam Rees in 1999, or when was that? He just won the Nobel Prize for this, right? Just like a few years ago. So the point here is that if you really want to be confident in the type 1A supernovae that you're looking at the edge of the observable universe, then you really better understand the type 1A family of supernovae. And the way that you do that is by discovering and characterizing in excruciating detail the nearby type 1A supernovae so that you can properly calibrate the ones that are very far away. So that's the kind of business that we're in right there. And we're playing, you know, as big of a role as we possibly can. And it's really exciting for us. So let's see. I think I'm running out of time. Is that correct?
Almost.
Almost. Okay. So maybe I'll skip through. I'll skip through a couple slides here. This is the stuff that I could talk about forever. Oh, I will say that here's a paper that had just been published. Jacobson Galan is the author's name. Did I write that anywhere on here? I have so many. Oh yeah, there it is on the top.
Yes,
Sorry.
it's behind. We can see that.
Gotcha. So this was a recent paper of this calcium strong transient, which is a weird class of what they think are type 1A supernovae. And it's a double peaked light curve. And you can see the stars here are all Thatcher data. And we were able to catch this second peak here right in the window between these X-ray detections, which made a huge impact in the professional community. And this is a fantastic paper. You check it out. If it's a kind of a beast, I have to admit, but it's a really cool paper with all kinds of great illustrations. And so, you know, the ability for us to change our observing program on a whim is really like what makes us scientifically viable and really able to contribute meaningfully to the professional community. Okay, so let me skip through. We do monitor BOYAJIAN'S star. This is 4 years of data. I'm going to just skip over this. And we also ended up in Tabby's second paper on BOYAJIAN'S star. And this is a student of mine that was working with us at the time. And some Thatcher data here shows up in the bottom left. But here's the cool part I wanted to just kind of end with is just last year, we had a student who really took the astrophotography program to kind of the next level. And it's a little bit challenging because we have a science camera. It's totally tuned to doing precision photometry. It's not, you know, it doesn't have the bells and whistles that you would want for a camera for doing astrophotography, but we do have a LRGB filter set. And we've been refining our techniques and you know, poking around at really exciting targets. This one obviously is a really famous one that I'm sure you guys all know, M51. And it's been great. You know, our pixel resolution isn't fantastic. It's only a 4 megapixel camera, 2K by 2K, but we can still do some pretty fun stuff. This was a snapshot of Comet Neowise that we took. Actually, it was just kind of fun. That was the comet that was that last summer? I think it was last summer that came by here just, you know, on a whim. And this was a really cool image. The colors I tried to get as true as possible. The blue is definitely like ionized molecular and atomic emission. And the red, I probably think should be probably more white. But at any rate, the color gradient there is actually real. And it kind of exposes some of the physics that's actually happening in chemistry that's happening in this comet. This Bode's galaxy, kind of a fun one. The seeing wasn't particularly good on this night, but it's a pretty impressive galaxy that fits nicely in our 21 arc-minute field for our camera. Pac-Man Nebula, which is pretty fun. And these, by the way, these were all done 100% by a student using PixInsight on the back end with our LRGB filter set. So pretty impressive for a high school kid to really dig into this. Another famous one, Orion Nebula. Yes, I wanted to, before we go here, I just wanted to say that we have been shut down here for a year or more, but we will be looking forward to having open observatory events where we can invite people up. And if you are interested in coming up, checking things out, we have an eyepiece. We can check things out on the sky on our 0.7 meter. And so, yeah, keep your eyes out for that if you're interested. We'd love to have you up. And yes, just continuing the sense of wonder and promoting the appreciation of the dark skies that we have here in Ojai is of primary importance. So I'll end there, and yeah, if you have any questions, I'm happy to fill in any gaps or elaborate on any of the things I talked about. Thank you, guys.
Dr. John Swift, thank you so very much. Thank you. Great talk. Great talk. Now, I may have a few comments later on, but let me leave this to any questions. I'll save my comments for the very end. Questions, Reza?
Yes, let's start with our panelists. I see Janelle has a question. Why don't you go ahead and ask it yourself, Janelle?
Oh, okay. Now, I was looking at, the picture that he had shown of the, like the first picture once they revamped the observatory of that galaxy, the spiral galaxy. My question, which, I seem to ask several people, nobody can ever really give me an answer, but when we're looking at the Milky Way galaxy, we're looking through the plane of the galaxy. So if we're looking at the Milky Way through the plane of the galaxy, how do they know it's a spiral galaxy? I mean, how can they tell it's a spiral galaxy? I mean, do they just say that because that's kind of the best looking one? Or
that would be fairly vain, wouldn't it? Yeah, no,
if
that's
you're looking at it through the plane of the galaxy, how do they know it's a spiral galaxy and not just, one of the million other shapes?
It's a fantastic question, and there are good answers to that. Actually, there's very good reasons why we believe it's a spiral galaxy. So one of the first ways to convince yourself of that that you can do without telescopes or experts actually is you can go out on a really dark night and you can look at where the Milky Way occupies across the sky. Mm-hmm. And it only occupies a strip, one flat strip that goes across the sky. And so if we're submerged in that galaxy, and let's say we were in some kind of elliptical galaxy or something, that's not what the galaxy would look like. It would not be a strip across the sky. So the galaxy we know is flattened. It's very flattened. And another thing that you can tell is that when you look at, if you go to a really nice dark sky, you can see dust in the plane of the galaxy. It obscures the light of the background stars in these big dust lanes, we call those. And we know, like, for instance, elliptical galaxies, they don't have dust like that. But this is something that is very characteristic of a spiral galaxy, as well as things like the Orion Nebula, where you have these massive star-forming regions. That's a spiral characteristic. All those things are things that you can see. But the thing that's really convincing that you can't see is if you look at the hydrogen gas in the galaxy. Mm-hmm. Okay. In particular, there's a very interesting emission mechanism for hydrogen where you have neutral hydrogen and the spin of the electron can flip with respect to the nucleus. And that spin flip gives you radio emission. And that radio emission you can see all the way across the galaxy. And the interesting thing about that is that with an emission line, you can get the velocity of the gas. So you can map out the motions of the gas in the galaxy, and you can infer the distances to that gas. And what it maps out is a beautiful spiral pattern. So it's a pretty solid conclusion. And then of course the
gas answer.
yeah. So another
that one.
good. And another thing that you might keep your eye out for, Janelle, is the Gaia satellite, which is taking the positions of billions, or maybe at least billions of stars in our galaxy.
Mm-hmm.
And to almost all the way to basically to the galactic center. And those positions are I will map out a spiral pattern as well. I think you will see. So yeah, it's a great question.
Okay, cool. Thanks. You're the first person that's ever given me an answer. I appreciate that. Thank you.
You're welcome.
Thank you. Great. Next question is about the exoplanets. That the research you mentioned you're doing there. Can the moons around the exoplanets be detected using this transitioning method?
Yep. Yes, that in principle, that it definitely can be done. And in fact, there's a really brilliant astrophysicist at Columbia named Dave Kipping, who has spearheaded this exomoon project. And he started it back in the Kepler space mission days, where he had that exact thought about whether we can detect moons around planets and what that would actually look like. And so he has a whole series of papers that are detailing exactly what that would look like and how we would be able to tell that they were exomoons, not exoplanets. And he has yet to find one. So I don't know what that means necessarily, but this is an idea that is really exciting and has been thought about in gory detail. And you could probably look up Dave Kipping. Actually, he's a well-known astrophysicist, and he has a public, he has a lot of public. He's got a Twitter account and all that business. So if you want to learn more about the ExoMoon project, I encourage you to seek him out.
Excellent. Thank you very much. And now the next question is about the level of automation in the observatory. You mentioned that it's automated. How automated is that? Do you have any permanent staff there on the location? Could you fully operate it from internet, or can you explain more about that?
Yeah, great question. Yeah, that's a big piece of it, is the automation. And it was kind of the pain in the butt, to be honest with you, to get it all running. And it's, there's a lot of moving parts. So has been working really well lately. So, but I'm always nervous to say that. But I have had kind of catastrophic failures now and again, partly my own fault, partly just, just sort of Murphy's Law kind of stuff, like anything, anything that bad that could happen will happen kind of thing. But it is when it's running and it's built to be in principle fully automated, that doesn't need any intervention until you need to grease the sprockets. So the primary software that we use to automate the observatory is called the Astronomer's Control Panel, ACP. It's a big suite of software written by Bob Denny that follows ASCOM protocols. So all of our equipment is ASCOM compliable or compliant, and so that's the master software that sits on top of the telescope control software, the camera control software, the weather software, the dome control. Like there's all this stuff that is underneath that. And it's taken a while to get all the bugs worked out, but it's 100% automated. In fact, like I said, I'm always nervous to say this because I am the only one here that has to fix all the problems when they go wrong. But it's been 2 months since I've touched it, and every night it just runs. And the only thing I do is I'll adjust our queue. I will put new targets in our queue, or I will adjust our queue based on the data that we have, and that maybe we've watched a supernova and now we're not detecting it anymore because it's too dim. I'll just disengage that program. But that's the amount of interaction that I've been doing for the last couple months. There are times when I'm like dealing with failures constantly for a week straight. So it's the idea is that it's totally automated, but of course things will go wrong.
Now, since you mentioned about queuing, so how's that done? Is that manually you choose which order it goes, or do you have an automated AI system that does that?
Yeah, it's not AI. It's a dispatch scheduler. So it's not a queue scheduler that you set up your targets and you just kind of knock them out. It's actually a dispatch scheduler, and this is also a piece of code that I think Bob Denny wrote that too. If he didn't, he's definitely he's very knowledgeable about it. And essentially, what it does is that we have a list of objects, and they all have their constraints. The obvious ones are just right ascension and declination and what time it is, right? Whether they're up or not. But there's a whole host of other constraints, and you can even attach a priority to a particular target. Like the ones that we're like, we have to observe this every night. We boost the priority like really, really high. You can also put constraints like air mass constraints or hour angle constraints or all this stuff. And then it's just this giant program that kind of does, some, crazy version of the traveling salesman problem, and just figures out, okay, here's all the targets. Here's what we want to do. Here's the most scientifically important ones. Here's the ones that we can do. And then it just figures out what's the optimal next source to observe. And it does that every iteration. So then once it finishes an observation, it goes through the whole thing again. It takes the whole queue. It considers everything. Where are we at? What time is it? What are the highest priority targets, et cetera, and then goes and finds the next one. And this is really just made possible by the amazing computer power that we have available at our fingertips, that those computations can be done in less than a second. So, and I have about almost 5,000 targets in our dispatch scheduler right now. So it's pretty cool.
And how do students get access to that? Is there a web interface that they put in their orders? Okay.
Yep. Yeah. In fact, there's a very convenient web interface. So the students here at Thatcher, we kind of are a bit more hands-on, and I will take the students up there and we'll actually get on the control computer. And, I like them to actually, give them that ownership and, instill a little bit of fear in them about like breaking things, even though they can't really break anything, but, just giving them that experience of controlling the facility. But we also there's a web interface that the ACP software comes as, there's a web server available. And so for instance, we've been collaborating with a class at Stanford, a physics class, who had to shut down their observatory for COVID. And we've been lending time to them on our telescope so that they can run their physics class. And we've worked it out in a way that it's mutually beneficial. So we have the Thatcher students present the observatory to the Stanford students so that they get all the details about the observatory. Then the Stanford students actually write an observing proposal for the telescope. And then the Thatcher students read the proposal and then comment on it and then give them that feedback. So it's giving them a little bit of, a real world sort of situation where there's like a time allocation committee and you need to really think about your project before you apply for it. And so that's been a lot of fun. And then they just operate it through the web interface and it's really smooth.
Excellent. And now some instrumentation questions. First of all, what happened to the 24-inch Cascarian telescope that was first in the dome?
So I have a limited knowledge of where it went, but I do know that it went to Besant Hill, or it was the Happy Valley School at the time, which is kind of right across the valley here. And that lasted not very long, just a couple of years, I believe. And then it went to I'm blanking on the college down there in Santa Barbara, the Catholic college. Westmont? Is it Westmont College? Gosh, I forget. Okay, there's a I'm blanking. I think it's Westmont.
Isn't it Montessori?
That doesn't sound right to me. I thought it was, yeah, I should probably just Google it really quickly. But it's the nice one, you know, where you're driving down, you're kind of coming out of Montecito and it's on the right. If you're going north on the 101, it has a nice lawn and it's kind of up on the hill.
That's Westmont College.
Westmont College.
That is Westmont College. I visited the campus. I know what you're talking about. Yeah.
Okay, awesome. So it went there for a while. And that's kind of where I lose it. Like I don't know how long it stayed there, and I'm pretty sure it's not there now. It's probably, yeah, what's his name? John Lewis, I think, from SSP. He's kind of one of the historians, and he has a whole collection of telescopes. He would know where it is actually, but I don't know what happened to it. Interestingly, I'll give you, since I don't really know the answer to your question, I'll give you an interesting, another little snippet. There was a twin telescope, 24-inch, that was built at the same time at Caltech that went up to the White Mountains on the east side of the Sierras that I think is still there. But it did science for a really long time up in the White Mountains. And it was kind of like the sister telescope of Thatcher. But I don't know. I don't know where that thing ended up. It'd be great to know.
Okay, thank you. So does the CDK 700 have a field rotator on the alt axis?
Yes, it does. We have there's a focuser rotator combination little unit that sticks right on the port there. So for the instrumentation people, so the CDK is a corrected Dahl-Kirkham design. So it's actually an ellipsoidal primary. And then there's a spherical secondary, which has nice properties, right? The alignment's very easy with a spherical secondary because you just plop it on there and it's aligned. And then there's a flat, a tertiary mirror that's at a 45 degrees and it's on a little rotator. So there's it's a dual Naismith ports on the CDK 700. So we have on one side we have all our science equipment. You know, we can just direct the light into that port. And there's two small lenses in the port that's the corrected part of the Dahl-Kirkham to get better focus over the whole field. And then, or we can rotate that third mirror to the other side. And currently we have just an eyepiece on that side. So it's really cool because we can do a bunch of science and then we can be like, oh, let's go look at the moon or whatever, you know, and just push a button and then just go look through the eyepiece. And it's really, it's a pretty slick design. So, so on the side that we have all of our instruments, the first actual piece of equipment on that port is the focuser rotator. And so, yeah, we can track for all night long and without, you know, smearing or anything like that. We have the capability to guide, but we rarely do because the mount model is really solid and on each axis, on the azimuth and altitude axes, there are like 80 million encoders. It's a direct drive motors, so there's no backlash. It's just like magnets on magnets. And then there's a little laser that reads off the encoders, and we have like an 80 milliarc second accuracy on each axis. And so, so we can take, without guiding, just tracking, we can, you know, just go to the source and we can take a 5-minute image and there's just no sign of smearing at all. So it's pretty cool because guiding is just a pain in the butt to, you know, to acquire the sources and to get it really set up is a pain. So that's another actually important point for this automation is that we don't need to guide. We can just track.
Excellent. Now, next question wants to know what's the magnitude limit for your supernova survey?
Great question. So we've kind of just figured this out, and it's right. We take 1 minute images. Our science images are 1 minute long, and with a 1 minute image, of course, it depends on the seeing. So the worse the seeing is, then the shallower the image becomes because the light is spread out over more pixels. And it's also background dependent, right? So if the moon's up and fairly close, that will vary things. On the best nights, best seeing, darkest sky, we can get to a little better than 20th magnitude in 1 minute. And then, but I think standard, if you really want to be confident in the thing that you detect, it's probably about 19.5 or something like that is about our limit.
Thank you. And next question is that the questioner mentions that they're using this rochesterastronomy.org website to get the alerts for the visible supernovae. Do you contribute your results to this site?
I don't contribute we don't contribute to that site in particular. And I'm not familiar with that site actually. So I'm not sure exactly what where that fits in the whole variable source kind of notification system is. But we mostly go through ATEL, the Astronomer's Telegram, and TNS, the Transient Name Server. And then those are the two big ones that we use to get the information. And then we mostly follow up targets that are already in those databases. So we don't have, we have never updated any of those databases with our own discoveries. So I hope I didn't mislead people here, but like we have detected supernovae. And if there were no other telescopes in the world, we would have discovered them. But we have not actually discovered supernovae because there are many supernova surveys going on that are actually more powerful than ours. So up to this point, we have only been contributing to the ones that have already been known.
Thank you very much. This concludes all the questions. Now back to Keith.
Well, Dr. John Swift, it has been an honor to have you with us tonight. I don't have any questions for myself, except to say that one of the benefits that we provide our members are exclusive behind-the-scenes tours. Do you think that would be available for VCAS members since we're now starting to come out of this COVID shutdown?
Yeah. We have, I don't know what our latest policies are right now for COVID, that we're in flux here as the students are leaving campus. And we've been on a pretty strict lockdown for a year. So once all these, once things become more clear about, what the protocols are going to be for having visitors on campus, et cetera, that would definitely be something that we could offer. Yeah.
Fantastic. I have your contact information. I'll stay close with you, and I'll make sure that Orange County astronomers are part of that group as well, because I'm sure some of them would like to drive all the way up to beautiful Ojai and get a nice look at the night sky through the Thatcher Observatory. I want to thank you again. Gentlemen, David Contreras, Todd Mitchell, John Rogers, Reza, any last comments from anybody?
I had one, John. Have you fixed the roof yet?
Oh, yeah. We have not. Yeah, we've not fixed the roof, but yeah, I kind of, it's one of those things that I just pretend it's not there because it doesn't affect our observations yet. So yeah, what Todd's talking about is a funny miscommunication between a subcontractor on campus who was updating our walkie-talkies that our facilities department use. And the subcontractor, I don't know what was going through their brains, but they put a repeater antenna on the roof of the observatory, like obscuring the field of view of the telescope. Just randomly, I walked up there one day and was just like, what in the heck is going on here? So yeah, I ripped that thing down, but it was bolted into the roof of our observatory, and it's a PVC roof, and they use tar and tar and PVC don't play well together. So I've been just ignoring that thing, but eventually I'll get up there and do something about that. Yeah.
Sounds like a mess. So next month, to everybody who's here right now, we don't have a speaker scheduled just yet. And we do plan that in July and August, we will be on complete hiatus. It's going to take some energy and some planning We just can't just jump right into things and open VCAS up right away. It's going to take some steps. However, I wanted to mention something. I noticed that you had Tabby BOYAJIAN in the mix there, and she's part of Tabby's star, right? She's what we call
that is Tabby. Yeah,
that is Tabby.
Discovered it.
And then the very interesting thing is that what I'm hoping for, I'm making no promises, but I know Will Henry, who was the writer, producer, and led the team that created the documentary, The High Frontier, which was just recently released on the Science Channel. And that is about Gerard O'Neill and his habitats in space. This documentary, which I've already seen, features the last interview with Dr. Dyson, the Dyson Sphere. So I'll try and get that link out. I've had the link out to people before. I'm trying to get them, not to upstage you, John, but there's a common element here between Tammy BOYAJIAN and Dr. Dyson, because Dyson is the one that came up with the Dyson Sphere to explain the fluctuations of the Tabby star. I thought that was interesting. Other than that, Dr. John Swift, looking forward to seeing you again and bringing a whole flock of VCAS and OCA members up to Ojai to check out the Thatcher Observatory for ourselves. And other than that, is there anything else you'd like to say before we call this meeting a close?
No, thanks for having me. It's been a lot of fun, and I'm glad I bumped into Todd up here. And thank you for sending the calendar. And yeah, it's been a pleasure. Thanks for having me.
And I will keep you in touch with John Rogers as he learns he can help you fill out some of the gaps in the history. And I see him nodding his head. To everybody, that concludes our meeting for this month. Thank you for all being present. And I'll see most, if not all of you in the meeting afterwards. Good night, everyone.